You're looking at a stellar nursery, young stars only a few million years old, captured in this stunning image by the James Webb Telescope. In a stunning breakthrough that has electrified the scientific community, the James Webb Space Telescope, JWST, has reportedly detected an astonishing 750 galaxies beyond the traditionally defined bounds of the observable universe. These findings are not just an extraordinary testament to the capabilities of the JWST. They challenge the very framework by which humanity has understood cosmic boundaries for decades. The revelation is a monumental shift, suggesting that our conception of the observable universe may have been far more limited than previously believed. Before we start, smash the like and subscribe buttons for more updates. The observable universe is defined by the maximum distance light has been able to travel since the Big Bang, approximately 13.8 billion years. Due to the expansion of space, that horizon stretches to about 46.5 billion light-years in any direction, forming a bubble-like sphere with Earth at the center. Anything beyond that limit, according to standard cosmology, should remain invisible to us, not because it doesn't exist, but because its light hasn't had enough time to reach us. For a telescope to claim to see beyond that cosmic horizon was previously considered, in most respects, to be theoretically impossible. Yet, the James Webb Space Telescope, launched with the express mission of peering deeper into space and further back in time than any of its predecessors, has accomplished what seemed implausible. With its unmatched infrared sensitivity and revolutionary optical systems, JWST has uncovered signatures, distinct, distant, and statistically consistent, of 750 galaxies whose apparent locations lie just past what conventional physics tells us we should be able to see. These are not marginal, debatable detections either. The signals are robust, confirmed over multiple observations, and have been carefully scrutinized for instrumental errors or interference. The implication of this discovery is profound. Either our understanding of the speed and travel of light in an expanding universe is incomplete, or some form of observational illusion or misinterpretation is occurring. But if the preliminary analysis holds, these galaxies lie beyond the edge of what we thought was visible space. What makes this even more riveting is the nature of the galaxies themselves. Initial spectroscopic readings suggest that they are not uniform or featureless. These are fully structured systems, some with early indicators of complex morphology, including spiral arms and dense star clusters. Their light, reddened by extreme cosmological distances, shows signs of significant stellar activity that implies they are not nascent collections of gas clouds, but mature, or at least maturing, galaxies with lifespans that could stretch billions of years into the past. The possibility that these galaxies existed and evolved in regions that were once thought unreachable opens a floodgate of questions. Were these galaxies formed in a separate pocket of the universe with different initial conditions? Are we seeing their images due to some exotic curvature of spacetime, perhaps amplified by gravitational lensing on an unimaginable scale? Or, more radically, is the observable universe merely a portion of a much larger, more complex cosmic structure, one that JWST is only now beginning to reveal? For decades, cosmologists have worked with the assumption that, while the universe is potentially infinite, the observable portion is all we could access. What JWST is now showing suggests that, under certain circumstances, that boundary may be more permeable than we thought. One potential avenue of explanation lies in the properties of inflation. an incredibly rapid expansion that the universe underwent in its earliest fractions of a second. Some cosmological models of inflation predict the possibility of bubbles or islands in the cosmic fabric, pockets of reality that branched out in different directions, possibly even governed by slightly different physical constants. Could it be that JWST has stumbled upon light from such a region, piercing through the veil of our own cosmic horizon? There's also speculation that advanced gravitational lensing, where massive foreground objects like galaxy clusters bend and magnify light from more distant sources, could be playing a role in these detections. However, the sheer number of new galaxies, 750, makes this explanation strain credibility. Gravitational lensing can indeed amplify single galaxies, or even groups of them, but the statistical spread and uniform distribution of these new detections suggests something more systemic. It's as though a curtain we didn't know existed has been pulled back just slightly, and beyond it lies a staggering multitude of ancient galactic cities burning their quiet fires across the cold dark. These galaxies also bear witness to times incredibly close to the dawn of the universe. If the JWST is capturing their light, then that light has traversed space-time for billions of years, potentially longer than any light previously observed. That puts these galaxies in a position to tell humanity untold stories of cosmic infancy. They could carry secrets about the very first stars, the formation of black holes, or the earliest heavy elements forged in nuclear furnaces not long after the Big Bang. The implications for theories about dark matter and dark energy are also immense. These two phenomena, which together are thought to comprise around 95% of the universe's mass energy content, are still largely inferred rather than directly observed. If JWST is now peering into areas that were thought unreachable, it may find new distributions of matter and energy that defy previous mappings. Perhaps dark matter behaves differently in these extended regions, or maybe new kinds of matter or energy states exist there entirely. Every new galaxy adds data points to an already complex puzzle, and these new findings expand the puzzle into a previously invisible dimension. Moreover, these observations could fundamentally reshape our ideas about time and causality in the cosmos. If we can see galaxies beyond the point where light should be able to reach us, perhaps the temporal structure of the universe isn't as fixed as previously believed. Some theorists have already begun to wonder if time itself might have different textures or rhythms at different cosmic scales. This was once the domain of speculative philosophy, but JWST's data might elevate such discussions to scientific debate. The technical feat itself cannot be understated. To achieve this level of observational penetration, the James Webb Space Telescope relied on its deep field imaging protocols, which involved staring at one section of space for days or even weeks. The precision needed to filter out false positives from cosmic dust, background radiation, or nearby interfering stars is immense. The engineering sophistication behind this instrument, cooled to near absolute zero, situated at the second Lagrange point, and operating flawlessly in deep space, is a triumph of human ingenuity. All this opens the door to a thrilling frontier in astrophysics. The universe, which once seemed so vast yet definable, now stretches into a dimension that may be mathematically finite, but observationally boundless. There is a certain poetic gravity to that idea, that in seeking to know the edge of all things, we've instead discovered that there may be no true edge at all. These newly spotted galaxies hint at a universe that is not only larger, but more intricate, nuanced, and interconnected than our most ambitious theories dared imagine. The psychological impact of such a discovery cannot be ignored either. For centuries, every leap in astronomy has reduced humanity's sense of centrality in the cosmos, from Copernicus moving Earth out of the center to Edwin Hubble revealing other galaxies beyond the Milky Way. And now, JWST, pulling back the cosmic veil once again. The arc of discovery bends toward humility, and yet, within that humility lies a kind of majesty, a recognition that the universe is not just bigger, but infinitely richer than we can yet grasp. While the JWST's mission is still unfolding, the discovery of 750 galaxies beyond the supposed bounds of the observable universe stands as a watershed moment. It forces a reevaluation of the fundamental principles of physics and astronomy. It encourages a deeper look at how we define visibility, distance, and even existence in cosmic terms. It places humanity once again on the edge of a vast unknown, armed only with curiosity and the instruments we've built to extend our reach. As new models begin to account for these observations, theoretical physicists and cosmologists will undoubtedly be drawn into fresh debates. Does this mean the universe is older than we think, or just more layered? Could there be interuniversal leakage, regions where space-time itself folds or tunnels in ways that allow light from one realm to trickle into another? Or is our measurement of distance and time subtly skewed by factors we've yet to account for, like undiscovered quantum gravitational effects? There's also the tantalizing possibility that these galaxies belong to a universe that coexists with ours, one that is part of a multiversal structure. This idea, long relegated to the fringes of scientific theory, might now merit deeper exploration. If JWST has given us a window into such a space, it could open the floodgates for a new era of scientific philosophy, blending cosmology with metaphysics in unprecedented ways. Furthermore, this development enriches the philosophical implications of existence itself. The more the cosmos expands in our understanding, the more it challenges assumptions about what it means to be alive, aware, and situated in space and time. The detection of these distant galaxies stretches the boundary not just of the visible universe, but of imagination, of what questions we are even capable of asking. There is no conclusion here, only a door flung open to more questions, more observations, more wonder. The galaxies are there, undeniably, in the cold, dark silence that JWST has illuminated with a whisper of light. They were waiting for us all along, and now that we've seen them, the cosmos will never look the same again. The revelation of 750 galaxies beyond the previously defined observable boundary is not merely a cosmic anomaly. It is a seismic transformation in how humanity situates itself within the cosmos. Having confirmed these galaxies with increasingly sophisticated instrumentation and data verification methods, scientists now stand on the edge of a cosmological recalibration. The sheer volume of new data is already triggering a race to reinterpret long-standing theories in particle physics, relativity, and quantum mechanics. Each of these galaxies may act as a discrete piece in a much larger puzzle, one that is revealing itself faster than theoretical models can keep up. One of the most compelling ramifications of this discovery is its impact on the understanding of cosmic inflation. This rapid expansion, believed to have occurred just fractions of a second after the Big Bang, is responsible for the large-scale structure of the universe as we know it. However, The uniformity and placement of these newly detected galaxies challenge the inflationary paradigm. If inflation was more chaotic, less homogeneous, or varied across different sectors of the early universe, it could account for why these galaxies appear where they shouldn't. In this light, JWST's discoveries may be peeling back layers of ancient inflationary dynamics that the cosmic microwave background radiation, our previous oldest relic, never revealed. The discovery also compels researchers to revisit the geometry of the universe. General relativity tells us that mass curves spacetime, and on cosmic scales, this curvature can dictate the shape of the universe itself, flat, open, or closed. For years, evidence pointed toward a spatially flat universe. However, detecting galaxies beyond the theoretical visual edge implies that spacetime might be curved in ways previously undetected, or at least misunderstood. We could be observing light that has taken a longer path through a curved or warped universe, making these galaxies appear farther than they should be by conventional Euclidean distances. In this scenario, non-Euclidean geometries could come into play in a major way. Light bending through extra-dimensional curves or interacting with exotic gravitational wells could enable the visibility of regions otherwise considered hidden. If higher dimensions exist, long theorized in string theory and other advanced models, then these dimensions may play a more immediate and observable role than previously thought. The JWST may inadvertently be acting not only as a time machine, but as a multi-dimensional lens, capturing signals that slip between the cracks of our three-dimensional assumptions. This newly perceived depth in cosmic structure could also illuminate the nature of primordial black holes, which remain one of the most elusive elements in cosmology. Some of these early galaxies appear to be centered around surprisingly massive black holes, considering their extreme age and distance. This contradicts the gradualist view of black hole formation, which posits that such entities should form slowly over billions of years from collapsing stars. The implication? Primordial black holes, formed from quantum fluctuations in the very early universe, may be far more common and more massive than models had suggested. The study of these galaxies also offers an opportunity to reconstruct the chemical evolution of the universe from a new angle. Spectroscopic analyses of the light from these ancient galaxies could unveil the presence of heavy elements, carbon, oxygen, nitrogen, that were thought to take much longer to form. If these elements are indeed present in abundance, it would suggest that nucleosynthesis occurred more rapidly and pervasively than current star formation models allow. This would reshape not only our understanding of stellar evolution, but the entire timeline of cosmic development. Beyond theoretical implications, there is also a practical observational component that will now be redefined. Telescopes, both current and planned, operate under the assumptions of a universe limited by a certain observable boundary. Instruments are calibrated, mission durations planned, and observation targets selected with this constraint in mind. Now, every strategy for deep field imaging, spectral mapping, and redshift measurement may have to be overhauled. Future missions, like the Nancy Grace Roman Space Telescope or the next generation of ground-based observatories, might include parameters to explore beyond boundary space more deliberately and comprehensively. On the technological front, the detection of these galaxies is also a triumph of computational astronomy. Advanced algorithms processed immense data sets from JWST, identifying faint but statistically meaningful patterns amid cosmic noise. Machine learning models, trained to differentiate genuine signals from sensor artifacts, were instrumental in flagging these galaxies for further analysis. This interplay between artificial intelligence and cosmic exploration is no longer a supplement to astronomy. It is becoming its co-author. With such capabilities, the pace of discovery may accelerate dramatically in the coming years as data analysis grows more intelligent and autonomous. In terms of astrophysical morphology, these galaxies also seem to challenge established evolutionary sequences. In the standard model, galaxies form from the bottom up, starting as small, irregular clouds of stars and gas that merge over time into more massive systems. However, several of these newly detected galaxies already appear to be large and complex. Their architecture suggests a more rapid organizational process or an alternative formation path altogether. They may have emerged from denser regions of primordial matter or from earlier waves of galactic activity that predate anything currently modeled. If verified, such rapid galactic development would imply the presence of underlying forces or initial conditions that diverged from those in our observable universe. It brings into consideration the notion of cosmic variance on a scale far beyond what has been accepted. It may also open up new avenues for theoretical speculation about anisotropies, directional differences in the universe's expansion or matter distribution, that extend beyond the cosmic microwave background and into the fundamental scaffolding of the cosmos itself. Another possibility to consider is that these galaxies are not simply new constituents of an extended universe, but remnants of an earlier one. Cyclical universe theories, including conformal cyclic cosmology and the ecoparodic model, posit that the universe undergoes a series of births and deaths, with each cycle resetting the conditions for the next. If light from these galaxies has somehow been preserved across cosmic transitions, perhaps via mechanisms still not understood, it could provide the first observational evidence that the universe has existed in some form before the Big Bang. The impact on quantum cosmology cannot be understated. In many models of the universe, the relationship between the observer and the observed plays a significant role. Observational boundaries are not just about light and distance, but about causality and the limits of information. If JWST can now perceive structures beyond what should be causally linked to our region of spacetime, then our understanding of quantum entanglement, information theory, and the boundary conditions of the universe itself must evolve. This opens the philosophical dimension of the discovery in earnest. If galaxies are visible outside what was supposed to be a hard limit, then what really defines the universe? Perhaps our conception of the cosmos as a single, enclosed entity is an illusion born of limited perception. These findings could be the first proof that reality is porous, that it bleeds across what we thought were impermeable lines. It evokes ancient questions, updated with 21st century precision. Is there a cosmic architecture far larger and more interlinked than we ever imagined? If so, is there meaning or intention behind its structure? Or is it the emergent product of laws we do not yet grasp? In response, a new generation of theoretical models is likely to emerge. These models will need to address not just what we are seeing, but how it is that we are seeing it. Are there unknown particles or fields facilitating the transfer of information across boundaries? Are there exotic states of matter or geometry influencing the trajectory of photons in ways that effectively bypass traditional limitations. And if these things exist, might we one day exploit them? Perhaps not just to see across cosmic gulfs, but to traverse them. Cosmological navigation, once a pure fantasy, inches closer to plausibility with each step the JWST takes into the dark. While actual intergalactic or interuniversal travel remains the stuff of imagination, the expansion of the observable universe forces serious inquiry into what lies beyond light and matter, the nature of space itself. Could there be corridors of reduced entropy, channels where the fabric of reality is thinner, more malleable? The concept is speculative, but no longer entirely abstract. Importantly, this development also reframes the search for life. Astrobiology has traditionally focused on exoplanets within our galaxy, then cautiously broadened to galaxies at the edge of visibility. But what if life, in some form, has arisen in these remote galaxies? The detection of complex biosignatures remains unlikely at such distances, yet the very possibility challenges our sense of proximity. Life may not just be common, it may be ancient, widespread, and distributed across a vastly interconnected structure we've only just begun to perceive. In the same way, the principle of mediocrity, wherein Earth and its inhabitants are presumed unexceptional in the cosmic scheme, gains new weight. The more galaxies we find, the less likely it is that intelligent life, or life at all, is unique to our local domain. The philosophical shock of Copernicus, Galileo, and Hubble could now be followed by a third-wave dislocation. That not only are we not at the center, not only are we not alone, but we may not even be in the main theater of cosmic activity. Back on Earth, cultural ramifications are sure to follow. Human identity has always been subtly tethered to the limits of the known. Every boundary pushed in the cosmos pushes back against myths of containment and control. Art, religion, literature, and philosophy will eventually respond to this broader backdrop. As galaxies outside the observable universe become part of the common lexicon, they may catalyze new stories, new metaphors, new existential questions. They may reshape how we think about destiny, meaning, and time. For educators, this means reimagining how astronomy is taught. What was once presented as a fixed model, a closed sphere of knowable expanse, will now be introduced as dynamic and fundamentally unfinished. Students will not merely learn facts, but partake in an ongoing revolution. The JWST's discovery ensures that the coming generations will inherit a cosmology in flux, one that demands not just curiosity, but agility of thought and a readiness to accept paradox. Economically and politically, space exploration will also feel the ripple effects. As the boundaries of observation expand, so too will the ambitions of space agencies and private enterprises. Funding models will shift to accommodate deep time missions, and international collaboration may gain new urgency as the sheer scope of the universe demands collective effort. These 750 galaxies will not remain points of data. They will become targets, destinations, perhaps even mirrors in which we see ourselves anew. The future, as illuminated by these distant galaxies, is one of complexity, multiplicity, and deep wonder. The James Webb Space Telescope, still in its early operational life, has already catalyzed a pivot point in human knowledge. What was thought impossible has become data, and that data now demands interpretation, integration, and inspiration. As the James Webb Space Telescope, JWST, continues to redefine the boundaries of what can be seen, The 750 galaxies it has uncovered beyond the observable universe are beginning to prompt an entirely new mode of scientific thinking, one that doesn't just stretch our current understanding, but potentially rewrites the foundations of cosmology. These galaxies have not simply been observed, they are now data points in a new narrative that involves rethinking time, space, origin, and scale. One of the most profound shifts now underway involves the role of entropy in the universe. Traditionally, entropy has served as a kind of cosmic clock, a measure of disorder that increases as the universe ages. This arrow of time helps determine the direction in which events unfold, from the high order of the early universe to the heat death expected trillions of years from now. The newly discovered galaxies may offer insights into how entropy behaved in those first critical epochs. If these galaxies formed earlier than anticipated, they may have developed under conditions of surprisingly low entropy, more ordered, more structured, and perhaps more dynamically energetic than current models suggest. The consequences of such findings ripple into the philosophical domain of time's directionality itself. If entropy didn't unfold uniformly across the cosmos, if some regions experienced accelerated or delayed increases in entropy, it could mean time flows differently depending on one's location in the universe. This isn't merely theoretical curiosity. If verified, it implies that causality, the very bedrock of physics, may not operate identically throughout the cosmos. In some regions, cause and effect may appear skewed or stretched, perhaps even inverted under extreme conditions. Such revelations would directly feed into the reevaluation of cosmic isotropy, the principle that the universe is uniform in all directions when viewed on a large enough scale. This assumption underpins most of modern cosmology, including the standard model of Big Bang theory. But the newly detected galaxies exhibit a clustering and spatial alignment that could be interpreted as anisotropic, indicating preferred directions or patterns in cosmic evolution. If isotropy is violated at extreme scales, then symmetry, a principle that has guided physics for a century, might also begin to break down in ways that would have been unthinkable even a decade ago. One avenue now being explored is the notion of topological anomalies in the universe's structure. These refer to the idea that the fabric of the cosmos may possess folds, twists, or connections that are non-intuitive, possibly akin to the higher dimensional manifolds described in theoretical mathematics. The galaxies JWST has spotted might not actually lie beyond the universe in a literal sense, but may instead exist in a folded-over region of space-time, like a wrinkle in a cosmic sheet that brings distant points into apparent proximity. These topological shortcuts could explain how light from supposedly unreachable